Alright. Well, welcome back to the video game stream where I make a video game from scratch because AI does not exist in this universe. We're all safe from the AI mega lasers. Thankfully, on our side of things, I don't know about how your universe is doing, but I'm making video games. Alright. So, let's go ahead and transition over and see where we left off. Okay. Let's see here. The camera's still doing something very silly. The collider on the Yo-Yo has now changed to be I think I called it a pillbox collider. However, collisions are doing this. They're doing something very interesting and very bad. Basically, it looks like a Looney Tunes. Like whenever they go inside the fight cloud, and then somebody gets spat out. So obviously some bad math is being done there, and that needs to be fixed. And I'm going to fix that math. Because what else am I going to do? Alright. So. What would really help here is if I had a physics stepping mode where it, like as soon as a collision happens, it pauses physics. I think that's what I want first before anything else. So pause on collision is another mode, and we're going to go ahead and set that to be the mode that we start with right now. So the pause on collision. In the future, you can make it so that it pauses on a specific collision. Like it pauses only when one of the entities is the main character, when one of the entities is the main character, and this other entity is the other thing being collided with. Right? Okay. So, and when we're in the physics step state, or whatever it's called, we don't necessarily always want to run the physics. So, for physics step state, in physics step once, we're going to detect the first collision and stop doing anything. Stop doing anything at all. So basically, we're going to resolve one collision, which happens here. And this, I guess I'll have this function return whether or not a collision actually happened first, right? So, physics, physics collision, we're going to return, let's just say Boolean for right now. And so this returns true if there was an overlap and some collision needed to be solved. Okay. Awesome. Okay, so we go back to physics. Okay. Oh, I just got some spicy food. Okay, so if solve collision and what's it called? Physics step state. Physics step state is equal to pause on collision. We're going to say physics step state is equal to pause, whatever that is called. Don't step. Maybe pause is a better word for that. Paused. I'm going to go ahead and change that. Don't step. Paused. All right. So we change it to paused as soon as we come across a collision. Okay. And probably when I go ahead and exit this loop, since we don't want to do any more collisions, probably, let's see, speed squared by next position. I think probably all I really want to do is, like I can have this, and maybe this is valuable. I think all I really want to do is step through it with the debugger to see what the values are, like why it's getting, what it's getting, why it's getting what it's getting. All right. Because clearly it's like it's a flip normal situation. So let's see, it would be this one and this one. So this is the code that's being used. Might help to know, let's see, blocks, okay. Yeah. Okay, not clear right away. I think it's time for the debugger. So let's open up that physics collision file. Not over there, please. Thank you. I'm gonna break on this. Oh no. We're gonna break on if the overlap is, you know what, if the overlap's greater than 0, I'll just rerun it. Okay, that'll be fine. All right, so we know there's an overlap. And then I'm going to rerun the solver to see why. Oh no. The debugger doesn't want me to see. Doesn't want me to see. What the heck? Step into. And then it just doesn't. Okay. You ready? So this is. I want to see the next. I guess I know it's. I know it's gonna be wrong, so I guess I might as well use this. Position A, forward direction A, pillbox A. Cosine theta. What is cosine theta? It's negative for some reason. That doesn't make sense. Right off the bat, that doesn't make sense. Because the collider, let's see. This is the forward direction this way. So this is the forward cylinder, and so here to here should be positive. This is the wrong.
It's Korean style.
I see. So feature position B here. It's the wrong subtraction order. So it's this. Don't step. I know, but it is though. I just made it. Pause on collision. Oh, right, that is not the thing I just made. Right. Let's pause. That's fair. Let's... Okay. So we got... Oh! Well, it paused. That's good. I can't see the colliders, unfortunately. But it's not doing the right thing. That's for dang sure. It looks like maybe it's getting the correct normal, it's just the wrong direction. So I want to think about that for a second. Toward B... Position A, Z. Okay. I don't see why this would be a problem. And I also don't see why this would be a problem. And I'm just gonna comment everything out except this part. Just pretend there's one cylinder up front. See what that does. So he's getting pulled in, which is the opposite of what we want. I'm a little bit confused. I should be flipping the normal, I thought. It looks like it's happening regardless of whether I flip the normal, which doesn't make a whole lot of sense to me. Oh, probably because I'm doing this. Okay. No, it's... well, okay. Yeah. So that looks better. I do want to still draw. Whenever physics is paused, I still want to draw the colliders. So let's make sure that's still happening here. Interpolate. Yeah, this shouldn't be here. Yeah. This should be called draw colliders. This should be called drawing colliders. Debug draw colliders on something. I don't know. That's fine. Do colliders here. And this should get deferred up here. Okay. Need to make sure the world is a part of this scope so that it can iterate over colliders or physics bodies. Okay, so now, yeah, now it still draws colliders even though physics is paused. If I step things, see, that's looking basically correct. The yo-yo is not allowed to go inside the cylinder here. Okay. Now, if I go to collision here, I'm not really sure why I shouldn't be flipping the normal. Yeah, so if the collision direction is pointed away from okay. Hold on. So okay, so the test character is A, and the obstacle is B. So yeah, it is this one. And well, let me see here. Difference is B minus A. Yeah, so it's toward B. And I am providing B minus A here. Yeah, I'm doing okay. So it should be toward B. And I should have to flip the normal. I see that I'm doing minus equals here, but I see. I need to flip it in this case, not the other one. That's, I guess, kind of obvious. I just want to make sure it made sense. Okay, so now I'm bringing in the other cylinder, and I'm going to turn off pausing here. Just see it go at full speed. Wait a second, what was that? Hold on. Yeah, okay. No. Stevenson block after return. Where? Oh, I see. Whoops. No problems here. Alright, yeah, so That's funny. Okay, yeah. So if I like whip around, try to hit it with the end, yeah, that works fine too. The only place it wouldn't work fine is if I were hitting a corner on the side. That would be awkward. Okay. So I'm gonna try turning this on, and I probably don't really have a good enough test environment for this case yet, but at least it shouldn't do anything really weird. Right. I mean, it seems like basically I've got it working the way I want it to. Okay, cool. Alright. It used to slow down faster than that, but I'm gonna... You know what, I know why that is too. Let me fix that real quick. It has to do with the... Where is it? The linear friction is... Yeah, linear friction is not high enough. Side friction's fine, I think. Yeah. I'm sort of emulating a friction curve here, with it being kind of hard-coded. I made some stuff to have, to have curves. I just haven't put it in yet because it doesn't really matter that much. But yeah, I think the... Let's see. So friction is slide friction times ground friction. The problem is that slide friction, when it's really fast, it's going to be very small. I mean, its formulation makes sense, but maybe just increasing that a little bit will fix the problem. So I just want to see it slowing down sooner. It just isn't. It just really isn't. And if I look at... Well, no. See, it's not gonna... Wait, what? Oh, right. Cool. Now I need a recast for this shape, which... It'd be helpful if I had a box raycast. So it looks like I'm doing raycast as well. Okay. Might as well just get it done. Alright. So, got raycast plane, raycast circle, raycast cylinder. I need a raycast box, which, let's see, I never... Never added one of those to this module. I really don't like doing box collisions, but a box raycast is not that complicated. I just don't remember how to do it. And yet, I don't know. I'm in a world without AI, but I'm not in a world without Google. So I think what I'm going to do is just try to figure out in my head for a second, and then I'll look it up if I don't figure it out. So I'm going to spend a little bit of time thinking about it first. Alright. So this module in my engine has a very specific pattern to raycasts that essentially allows them to have... They return a lot of information, particularly when they hit something, because it's just way more useful to have a raycast that gives you all this information back than to, have some bespoke interface that gives you the information back, and like normal raycasts don't do it. I think it's better the other way around. I think it's better to have like a more fully featured recast that you use all the time, so that data is always available when you need it. And then if you really need like if you need a faster, more optimized raycast, you can just write that on the side, which I actually have already done. There's a constrained plane or a rectangle raycast here. There's one in here, and there's also one in the math module, which is a little bit faster. Okay, so raycast. Let's call it box. Box is fine. The center of the box, I want the half width, half length, and the half height. That is all fine. And then I want the width direction, the length direction, and the height direction. And that is all I need for that. Now, I've done a box raycast before where I know that you're going to be doing a bunch of box raycasts in a row. There's this thing you can pre-calculate. And I'm not precluded from doing, I don't have to not do that. I can absolutely have optimized, say I need to raycast one ray against 10,000 boxes. If there's this factor that you have to calculate every time that requires doing a square root or something, square root's not the biggest deal, but if you can omit doing it 10,000 times, that's actually a pretty good optimization. So if I find that out, if I figure that out, or if I end up looking it up, I can just put it on the request, which is what I usually end up doing with stuff like this. If I have a request result pattern for an API, what I'll do is I'll put the expensive stuff sort of at the bottom of the request, where you're not expected to necessarily know the normalized direction of the ray or the length of it. You can just pass where it begins and where it ends as the request, into the request, and then the direction and length will get calculated the first time the request is used, right? And it gets saved to the request, and you just reuse the request, basically the pattern only doesn't work if you end up trying to change something on the request, which is just not how you're supposed to use it, so I don't use it that way. If I change something on the request, then I make a new request. Yeah. There's a lot to be said about being more protective. I'm a big fan, particularly of being protective in cases where I'm working on large teams or even small teams, really. Being you immediately have to be a lot more protective. I find, at least working with myself, that I don't need to do that as much. So it just makes things easier. When you're really, really, really protective, like, good on you, hardening your program and everything, but also you can overdo it when you're just working alone, right? And make it so that you're just wasting a bunch of time when you could be using making a thing. Okay. Let's see. So, if I remember the algorithm correctly, you try to clamp the ray inside the box, which gives you your hit location. The hit normal is not a given from that. You still have to figure that part out. But obviously, if you can't clamp the ray inside the box, then it's not a hit. I also don't remember how to do that one. Though, okay, if you think about an axis aligned... Let's open up Paint here. Maybe this will help me out. Okay, so imagine I have like an axis aligned box that it has these axes. Okay, so it's aligned like this, right? Okay. And I have a ray in space. Maybe it goes through it, maybe it doesn't. You can't even tell. Like, maybe it's behind, maybe it's in front. Can't tell from this. Let's assume it is going through it. Then I'm just asking myself, like, let's say from the center of the box, if I move along the x-axis in this direction and the y-axis in this direction and the z-axis in this direction to get to the beginning of the ray, how much farther have I gone along those axes than I actually can, right? Which is basically just you get the difference and then you... Is it that? Yeah, you get the difference and then you just sort of say, well, no, if I can't have gone any more than this far, so it gets clamped to being to here instead of to here, right? So I can't have gone any farther than this in the height direction, so it gets clamped to there, and then I can't have gone any farther in than like this plane here in the y direction, so it gets clamped to like out here or something, and I can't have gone any farther than this in the x direction, so it gets clamped to here, something like that. Oh wait, no, it would be like all the way down here, right? I guess that's pretty sensible. Then the question is that point like on the ray? Because if the ray didn't pass through the box, then we've just clamped a point, you know, inside the box, and it doesn't really help anything. when it's not axis aligned, then you just need to get the distance along each axis of the box. You know it up front when it's axis aligned, but you don't know it. So you need to convert it, basically converting it. You're kind of rotating the, you're essentially rotating the ray into the box's coordinate space. It's the same exact, it's the same math. Okay. Yeah, and then the only question left is, so I've clamped them. Now the question is, I guess, do I have a line segment inside the box, or do I have like 2 points on the edge, or like that? You know what I'm saying? Because like, okay, basically, I could have this box. Okay, and I could have this ray like this goes from here to here. If I clamp that, I could get something like this, which actually does pass through the box. So just because I clamped the beginning and the end, it's not going to tell me whether or not it passed through the box. In fact, in fact, if it passes through the box, is this even the way to go? I don't think so, because like, I could have something that like starts here, goes through it, and essentially it passes through right here, and it passes out right here. But the clamp of this point is just going to be like right there, right? I don't really want to clamp the point. I want to clamp it along the line segment of the ray. Well, okay, another way to think about it. I mean, kind of the same way. But imagine the box here. Just thinking about it one side at a time, maybe. Box has this here is a plane with some normal on the front of it. And so, you know, where does the ray intersect this plane is, I guess, the first question. And so what I am doing is I'm clamping it not to this face, but to this like I guess between this plane, and if the other side also has a normal like this, right, to the other plane. So I'm clamping it between these two planes, right? The ray passes through like this. I want to clamp it here and here. because that's where it passes through those planes. So in a way, this is kind of like a batched, like, rectangle intersection problem. Kind of, I think it is exactly that. I think it's a little bit simpler than doing a bunch of rectangle intersections, because essentially if this ray is it simpler? Not really. Well, if the line segment, if there's a clamped line segment that lies between every set of two planes, so that's 3 sets of two planes for front and back, top and bottom, left and right here. If there's a clamped line segment that lies between all of those two planes, then it does intersect. Doesn't necessarily mean it hits the outside, and still don't know what the normal is. So I get the feeling what's going to happen here is I'm going to figure out something that works. It's not going to be the fastest way to do it, and I'm just going to have to replace it with the fastest thing. But I don't know, maybe I'll just let it play out anyway. Maybe. Let's, yeah, I'm gonna try thinking, I'll just try between two planes and see what that looks like. Like what it looks like for the ray to sort of have a line segment between two planes. You know, just exploring that. Okay, so let's see. Okay. Let's take the box. Front center is going to be center plus the half length times the length direction. And box rear center is going to be center. Well, same thing, just minus, right? And you know what it is? I think it's the inverse length, if I remember correctly. I'm going to pre-calculate the inverse length of the ray. But I will wait on that because I'm not actually sure that's right. I think it's the inverse length because I think you want to divide by the length to get like the normalized point along the ray, which is how you tell whether the point is beyond the ray or within it. So let's see. This is going to be minus the ray origin. And then what is stiff? Two. Plane, this is, let's see, length direction. Okay. I need to make sure that we initialize the request before we do anything else. Okay. And the result. Cylinder. Box. Let's see. Instead of checking for less than 0 here, there's probably a way to check across all of them. Also, can you say array hit if it's like moving along the surface? Probably not. Probably checking if less than or equal to 0. But I don't know.
She got it.
Yeah, wait, there's no way this is right. I'm gonna look it up. I'm gonna look it up because I could spend. I could and have spent like half a day to a full day on a problem like this, and it's just maybe not worth it. So, let's see. Ray 3D box intersection. Let us see what the world has for us. Size the box. Cool math. I don't think math people are going to have the best answer here. This is axis aligned. I'm not. I mean, it's not that big a difference from axis aligned. You just like essentially just putting the ray into the like. I guess I could use that then. Okay. Super cool. Axis aligned bounding box. Yeah, there's in INV dir. That's INV dir. Okay. Let's see. Given the bounds theory of blah blah blah. You can see bounding box. I think bounding box intersection of 3 slabs. The slab is the region, the space between parallel planes. Yeah, sure. Intersect a ray against a box. We intersect the ray against each of the box's 3 slabs in turn. That is what I was thinking. Because the slabs are aligned with 3 coordinate axes, a number of optimizations can be made. The ray slab tests. Sure. Basic ray bounding box intersection algorithm works as follows. We start with a parametric interval that covers the range of positions t along the ray where we're interested in finding intersections. Typically this is in 0, infinity. We will then successfully compute the 2 parametric t positions where the ray intersects each axis aligned slab. We compute the set intersection of the per slab intersection interval with the current intersection interval, returning failure if we find the resulting interval is degenerate. If, after checking all 3 slabs, the interval is non-degenerate, we have the parametric range of the ray that's inside the box. Okay. Yep. The intersections. I also need it to return intersections that happen from inside. And I don't think this algorithm quite covers that, but I think it can be modified to cover that. Intersect P method returns true. The intersections parametric ranges return the optional arguments hit 0 and hit 1. The intersections outside of the 0 to T max range of the array are ignored. If the array's origin is inside the box, 0 is returned for hit 0. Each pair of planes, the routine needs to give you 2 array plane intersections. See, this is kind of basically what I was thinking, but like, example, the described by 2 planes perpendicular to the x-axis can be described by planes through points x 0, 0, x 0, 0, 0, and x 1, 0, 0, each with normal 1, 0, 0. Consider the first t value for the plane intersection t0, the parametric t value for the intersection between array origin O and direction d in a plane ax plus by plus cz plus d equals 0 can be found by substituting the ray equation into the plane equation. Sure, I don't need this part. Code compute the t-values of the sub-intersection starts by computing the reciprocal of the corresponding component of the ray direction so that we can multiply this factor by this factor instead of performing multiple divisions. See, that's what I was thinking. Anyway, that's what I was thinking, but I didn't remember how to do this. So note that although it divides by this component, it is not necessary to verify this is non-zero. If it is 0, IMVRator will hold an infinite value, negative infinity or infinity, and the rest of the algorithm works correctly. That is assuming you have, I guess assuming you're not compiling with fast math or something, probably they would mess that up. Is that in the... I don't know. Distances are reordered so that T near holds the closer intersection, T far holds the farther one. I don't think this is actually as optimized as I thought it was. Like, I think I could probably just figure this part out. This looks basically... Oh, shoot, sorry. This looks basically like what I wanted to do. Stop bumping the microphone. Cool. Let's see. All right. And division is just the negative sine distance plane divided by pointing cosine t. It's the only division in this process. But ray direction is in this. So if you take so negative sine distance to plane, so impact dist, negative sine distance to plane divided by pointing cosine t here. This is the main thing. The main optimization is just not dividing every time. And so Hmm. If we had the inverse ray direction, it'd be length direction divided by ray direction in each part. I don't think that's what you want. Let me, let's see, impact distance. I'll work it out on paper, because so I think it's time for just a little bit of EDM here. Actually, just kidding. I'm going to take a 30-minute break here. So whatever music this lands on, you know, whatever music it lands on is whatever music it lands on. Alright. I have decided that because streaming has not made me wildly popular on Twitch or YouTube in the last 2 weeks, or I guess it's been just over a week now, which is not shocking in and of itself. But also, the all-day streaming schedule that I wanted to do isn't really 100%. It's not reasonable. It is not a reasonable thing. I'm just going to go ahead and probably end the stream right here. And I'm probably going to switch to a sort of weekly devlog format, weekly devlog and weekly live stream format. I'll be probably posting my devlog. I'll probably make the devlogs over the weekend, post them on Monday, and then do my weekly live streams on Friday afternoon, probably. Anyway, I'm going to go ahead and end this one here and send it over to YouTube. So thank you for watching.